Good evening and a very warm welcome to all of you for this evening's seminar by Professor Arvind Kumar, one of the most eminent educationists of our times, who has been an inspiration to many of us. It's lovely to see so many of you join us this evening. I will first request Professor Shomak Raichaudhuri, our director at IUCA, to say a few words before I outline our thoughts behind the seminars on this education series and introduce Professor Arvind Kumar and invite him to speak to us this evening. So, Professor Shomak, could I request you to say a few words?
Thank you very much. I'm very, very happy that we are starting off this new seminar series on science education. Just to tell everybody about the activities of the Astronomy Center for Education at IUCA. We started off as a center that was funded partly by the Pandit Madan Mohan Malviya initiative of the Ministry of Human Resources, now the Ministry of Education. And initially, some of us wrote a proposal to start a teaching learning center here to help university teachers teach astronomy and related subjects in their institutions. Some of us, like Sanjit Mitra is here and various faculty members in IUCA. So we got this, and from the very beginning, Dr. Dhruva Saikia has been part of, in charge of this this center. The Ministry of Education not only gave us this center and funded this, but also funded a National Resource Center here for astronomy, astrophysics in the country is now located in ACE. So ACE comprises of these two together, and recently to our the center, we've added a branch of the IAU's Astronomy Education Center. Now, as part of the National Resource Center, there have been a lot of activities going on online in terms of courses that have been developed for the SWAYAM platform, Arpit. And in the Teaching Learning Center, we are about to embark upon really intensive courses to do with developing programs of astronomy teaching and teaching related research in the universities. Quietly, this building that you see in the poster was built during the lockdown period, completed, and now it is open for business. Our initiative was a little thwarted by this the 2-year lockdown period that we had, but we hope now we can start in full steam. I hand you back to Dr. Dhruva Saikia to tell you about this new initiative of these lectures on science education, and I'm so happy that our first lecturer in the series is the most distinguished Dr. Arvind Kumar. Saikia.
Thank you very much, Shomak, for this succinct introduction to the activities of the Astronomy Center for Educators. While focusing on education, we have tried to keep in mind both the conceptual aspects of the discipline, as well as the teaching, learning, or pedagogic aspects in different situations and settings. In our programs, we have asked ourselves, how do we make teaching learning more effective? How do we develop more balanced and robust testing and evaluation processes? And at the initiative of Professor Shomak Raichaudhuri's discussions with the associates last year, we had a mini symposium on online teaching and evaluation, which was very well received. We also wonder, how do we locate our discipline in the context of a broad-based education? Several universities, as you know today, are experimenting with liberal arts programs or have started it. Although the emphasis in most places has been on humanities, there are also exceptions to this. Ashoka is an example in the private sector, which is building up strong science areas as well. And IIT Bombay has started very recently a Center for Liberal Education, which not only incorporates humanities, sciences, as well as engineering, perhaps the first IIT to do so. And now we ask ourselves, how best do we locate astronomy in such broad-based curricula? To discuss many of these aspects, including the philosophy and sociology of science teaching, or perhaps the objectives of education itself, including theoretical questions related to the nature and development of science, steps for science to reach across the socioeconomic spectrum, in addition to fundamental and important pedagogic aspects, we have started this series of seminars on education, which Professor Shomak Raichaudhuri mentioned a little while ago. And as he mentioned, we are also very fortunate to have Professor Arvind Kumar as the first speaker of this series. Professor Arvind Kumar did his PhD in physics in 1969 at the Tata Institute of Fundamental Research, Mumbai. He was a visiting scientist at CERN, Geneva during 69-70 and at Westfield College, London, 1970-71, and a faculty at the Department of Physics, University Department of Physics, Mumbai, from 71 to 83. In 1984, he joined the Homi Bhabha Center for Science Education, a national center of TIFR, and was center director of HPCSE from 1994 to 2008. Post-retirement, he was Raja Ramanna Fellow till 2013 and taught at the University of Mumbai, Department of Atomic Energy, Center for Excellence in Basic Sciences, Mumbai till 2020. He continues his occasional involvement in HPCSE's activities till present. A very inspiring teacher, and you'll hear a lot about him from his students whom he has interacted and taught with over the years, including his colleagues at the HPCSE. His research interests span a wide range of areas in theoretical physics and science education. Likewise, his educational interests are varied from university through college and school stages and include normal teaching courses, materials development, student nurture, and teacher orientation. He played a central role in launching the Indian Science Olympiad program beginning in 1998. He was a member of the National Steering Committee for National Curriculum Framework 2005, and he chaired its focus group on teaching of science. He has received numerous awards and recognitions, a fellow of the National Academy of Sciences. He received a Third World Academy of Sciences Regional Prize in Education and the Insert Teacher Award 2014. In 2010, he was awarded the prestigious Padma Shri for distinguished service in the field of education. Today, as you can see, Mr. Arvind Kumar will speak on reasoning and explanation in science, a pedagogical perspective, I believe largely drawing upon examples from physics, and it's a real pleasure and privilege to have you with us today. So, Professor Arvind Kumar, could I invite you to kindly start off? Thank you very much.
Yes. Thank you, Professor Dhruva and Professor Somak. It's a great privilege for me to talk to this at this prestigious institution, and it's this new center that's coming up here. I'll begin with the talk. You know the title already. And I think the abstract was circulated, so I won't go through the abstract. And let me start with the talk. Now, in this talk, as the abstract has mentioned, we'll consider what kinds of reasoning are acceptable in modern science, what kinds are provisionally acceptable, subject to later experimental confirmation, and what kinds of reasoning are not acceptable at all. Now, this word reasoning, you'll shortly know what I mean by this. But within those acceptable modes of reasoning, we'll talk about some frameworks, explanatory frameworks, or you might say approaches that scientists adopt to explain various physical phenomena. Now, these frameworks differ considerably from across different subjects in physics, chemistry, and biology. So, the examples that I draw will be mainly from physics. Now, but before I begin, there are two disclaimers. First of all, this is a rather ambitious title, so I must give these disclaimers. First of all, the content level of the talk will not go beyond BSc and SC level. So if you're looking for very current sophisticated physics, you'll not find it here. It's more or less the textbook physics at the college and university level, about which I'll be presenting this analysis. And therefore, several statements made here, particularly concerning explanatory frameworks, may have to be modified for the current, very highly sophisticated current research. So that's one limitation of the talk. The other and even more important limitation is that it's a kind of brief very simplistic pedagogic exposition, which I believe will be useful to teachers and students. Actually, the subject is a very rigorous topic in philosophy of science. If you open a book on philosophy of science, any standard book, you will always find one of the important chapters in such books would be on explanation and the various analysis. You know, there's a deductive nomological model and so on, DN model of explanation, etc. We'll see such things in philosophy of science books. The exposition that I'm going to give will have very little to do with that. And therefore, the analysis is simplistic pedagogic analysis for use in education. It will not meet the high standards of a philosophical analysis. So both content-wise, it is limited to university level physics, but not much more. And the analysis is rather simple, that a physics teacher would do, reflecting on physics, what he or she would do. That's the sort of thing I have in mind in this talk. So it's very limited in scope, although the title of the talk looks very ambitious. Now, to understand what we mean by an unacceptable mode of reasoning in modern science, let's recall an example from history that people in astronomy would know even more than I do. Now, Kepler was a key figure in the scientific revolution of the 16th, 17th century Europe. And after a lot of analysis, years of hard work on the very large amount and very precise, of course, for that time, it may not be precise by modern standards, but there was a large amount of data gathered by Tycho Brahe, as all of you know, and he arrived at his now famous 3 laws of planetary motion. His discovery that the planetary orbits are elliptical was met with much dismay. There's a lot of opposition, both from the popular lay people, even from also people involved in science. The natural philosophers, as they used to be called in those times. Oh, why? Why was there so much opposition? Because it went against the then common mode of reasoning. It was something like that. That which is divine must be perfect. The orbits of planets around the sun are in the celestial domain, the domain of divinity. The circle is a perfect two-dimensional shape in nature. Hence, planetary orbits must be circular. Now, if you look at this is what I call reasoning. There's nothing wrong with its logic. Given its premises, there's nothing wrong with its logic. So for us, the problem is not the logic. It's not illogical. The problem is the premises. So this is what I mean by reasoning. Reasoning is logic plus some premises or argument. And we accept an argument if, of course, if the logic has to be correct, but not only logic, the premises also we should believe in, they should be acceptable to us. So that is what I mean by the word reasoning. Now, this kind of reasoning may seem strange to us now, but actually it was there for thousands of years, from Aristotle to Ptolemy to Copernicus. All the people, basically, this kind of reasoning, they subscribe to it. Actually, all of you know better than I do that the astronomy people, that the geocentric astronomy, they made wonderful innovations. The epicycle, eccentric, equant, etc. Equant was by Ptolemy and epicycle was by various people. Even Copernicus used it. And the whole idea was to retain the essential idea of circular paths, because that's what that reasoning said. So they had to abide by that thing, and they tried to fit the theory with all kinds of very brilliant modifications. Now, modern science does not accept this reasoning, not because it is illogical. As I said, it's not a question of logic, but its premises are theological. They invoke divinity, etc. And that is what is not acceptable to modern science. So in other words, it's not only logic, but also the premises that embed the logic that scientists examine to judge if an explanation is acceptable. Now, at this stage, I must say that I'm not exercising any value judgment about these premises. That's a different kind of debate. I'm only characterizing modern science. Modern science does not accept these premises. So the debate about these premises, theological, so that's not the idea, or that's not the point in my talk. I want to, as a physics teacher, characterize the reasoning of modern science, and modern science doesn't accept these premises. Now, still you might think this example is trivial because everybody knows that science does not entertain such reasoning. But there are other kinds of reasoning also that students probably would not know that science does not accept. Of course, all teachers know. But now, teleological reasoning is one such example in which a phenomena is explained in terms of purpose or the final. That's the word is teleological. It's purpose-oriented reasoning. For example, the statement, the student is working hard today to do well in the examination tomorrow, seems a perfectly sensible statement, explaining the present action in terms of the future goal. What's wrong with it? Anybody would say. It's so much a part of our daily life that we can forget that it is not acceptable in physics at all. In physics, we explain the motion of an object using the laws of motion and initial conditions. What they say, we have initial causality, not final causality, not in terms of any purpose or any final goal of the object's motion. But this was not always so. Teleological reasoning was common among natural philosophers who were you can say, preceded the modern scientists in history. For example, Aristotle, known to be a great mind in antiquity, he held that motion was of two kinds, natural and violent. And these violent motion needed an external force, but natural motion, unconstrained motion, was simply due to the inner tendency of the body to reach its natural state. Now, this is a very clear example of teleological reasoning. It was very much common in Aristotelian physics. And these, all of you know, I think the four basic elements had a natural hierarchy of places: earth at the center, water, air, and fire. Something well known about the elements in ancient history. A stone is predominantly the element earth, so its natural motion is towards its natural place. So this is how Aristotle was explaining the free fall towards the earth. And a corollary of this kind of reasoning, which we of course know is not incorrect, is that heavier stones would fall down faster than the lighter ones because the heavier stone has more of that element and hence that greater tendency. Now comes the scientific revolution triggered by Copernicus, Kepler, and all these other great figures in the history of physics, Galileo, Huygens, Newton, and others. And the basic point of scientific revolution was essentially the overthrowing of Aristotelian physics and its premises and its reasoning, especially the teleological reasoning. And with the phenomenal success what followed, teleology was banished from physical sciences. So this was a marked change. So sometimes we say the scientific revolution was a change in methodology. Of course it was experimental-centered methodology, but equally important, it was a change. It was overthrowing a mode of reasoning that was very much common in ancient science, namely teleological reasoning. Teleology, even after the scientific revolution, persisted in biology. Because in biology, the structure of an organ is so marvelously, tuned to its function that it is very natural to think that it was designed there's a creator behind it. It's very natural. It's a natural thing. It took the theory of evolution by Darwin and Wallace in as recent as mid-19th century, which was completely non-teleological, to throw away this idea. And the Darwinian evolution theory of natural selection says that the species evolve through the blind processes of natural selection, and they accumulate over time, and that's how species evolve. Evolution has no teleology, has no purpose. There is no end goal of evolution. And with the success of this theory, teleology was banished from all of modern natural sciences. So physics, chemistry, and also biology. Of course, it's not out from behavioral sciences, because behavioral sciences deal with something else. They deal with volitional domain, with people, and that's a kind of slippery thing for natural sciences. So I'll stay away from behavioral sciences, where of course you do talk in terms of will and motivation and things of that kind. I'm restricting to natural science. Sometimes you may feel that something in physics is teleological. For example, an important example is action principle. This is, as you all know, the action is an integral over a Lagrangian. Lagrangian is defined in terms of kinetic and potential energy of a mechanical system. And this is the action principle, that the particle takes a path such that this thing is an extremum. This is a, mathematically speaking, a functional of QIT, and this functional derivative is zero, with endpoint variations being zero as being the condition. This appears teleological. Actually, it feels that, well, starting at t equal to t1, how does the particle know? I mean, particle chooses a path so that the action at the end of it all is extremized. So it does put you in a little bit of dilemma, but it's resolved by the fact that is so-called this global law. It's a global object, not a local object. It's equivalent to a local law for the path, the Euler-Lagrange equations. And these are differential equations. They connect quantities with their derivatives at that point. These are local things. And there's no meaning of teleology there. So a local law is obviously non-teleological. Another important mode of reasoning in ancient times was anthropocentric reasoning, giving special unique status to us humans and by extension to the planet we inhabit, the Earth. This was a largely unquestioned view in ancient times. As we all know, Copernican revolution displaced the Earth from the center, and the Earth is just one planet, not just another planet, the solar system. And the solar system itself is among many numerous millions of such things, billions in the cosmos. Still, as far as biology is concerned, humans continue to believe in their privileged status in the cosmos. We must realize that the scientific revolution was more in astronomy and physics. The chemical revolution came a century later. And biology, I mean, this was really revolutionary in biology. So that came quite much later, almost just under 200 years later. So after that, of course, the privileged status of humans was banished as far as natural science is concerned. And this total lack of purpose and no special status for us in the laws of the universe is very nicely captured in the following quote of Steven Weinberg, who died recently last year. The more the universe seems comprehensible, the more it seems pointless and meaningless. There's no meaning in the universe. Natural sciences do not offer anything that you can say is associated with any purpose or with any something special for humans, and we just seem to be irrelevant to the laws of the nature. That is the quote of the great scientist Weinberg. Now I come to another mode of reasoning, the metaphysical modes of reasoning. Metaphysical reasoning assigns fundamental principles. So we were talking of theological, teleological, anthropocentric. Now we come to metaphysical reasoning. This is something that that, you know, it invokes ideas like unity, beauty, economy, parsimony, simplicity, and things of that kind, which you intuitively feel as a criteria for selecting a theory or for putting forth some ideas. Now, is it correct? Consider an example of metaphysical reasoning of the kind. First, I'll give you an example in ancient science, and then I'll give you an example even in modern science. Actually, whatever I'm saying was given by Plato, although Plato had only 4 elements in his mind, and 5th one was added by Aristotle and so on. But I'm sort of rephrasing that bit Plato's argument. There are only 5 possible regular polyhedra. This is a mathematical theorem all of us know. And even the Greeks knew this theorem at the time of Plato. It was known that there are only in 3 dimensions, there are only 5 possible regular polyhedra. I mean, they are, you know, 3-dimensional objects with regular polygons as their faces. It's 4 for tetrahedron, 6 for cube, 8 for octahedron, and so on. So these are the number of faces. And as for the polygons are concerned, most of them are triangles. Cube, of course, is square. Tetrahedron, octahedron, and this one is a triangle, and this one I think is pentagons. So whatever it is, there were 5 such things. And in ancient times, as we all know, there were 5 fundamental elements: earth, water, air, fire. That's what people believe, that those are the basic elements of nature by which the entire universe is made of. This coincidence was not to be regarded accidental, but suggestive of a basic unity of nature. Accordingly, Plato suggested, slightly rephrased, that the shapes of atoms of these elements had one-to-one correspondence with these regular polyhedra. Plato said exactly this, but for four of them. Now, this reasoning, again, you see, if we see it from our modern lens, then all this looks implausible, and I would not use the word ridiculous, but you know, I do not think we should use any value judgments on these, because you know, these were also brilliant minds in their own times. And however, it took a lot of, as Weinberg says, it was not so simple to get rid of those reasoning and arrive at the kind of reasoning and explanation. It needed a lot of displacing of old ideas. So within that framework, it was not bad, but although we might now think it's very implausible, because first of all, the atomic nature of matter was conjecture, it was not established, and of course not known to the extent we now know. But lest we should think that it's all over, it's not so. Metaphysical reasoning is there even in physics. Though, I mean, physicists don't like to use the word metaphysics. They may say speculative or conjectural or intuitive or whatever word they may use. Metaphysics is a bad word for many people in physics. But if you come to think of it, Einstein's attempt to unify gravity in electrodynamics was in fact, at least part, we'll have to agree that it's a metaphysical drive. Because he was eminently successful in uniting, you know, space and time and matter in his great theories. And there was unification earlier in the 19th century between electricity, magnetism, object. So unification was a kind of drive in physics always. But unless it is suggested by observations, it is metaphysical drive. But Einstein did it, and as we all know, it was a failed drive. But there is a difference between Einstein's attempt and the attempts earlier. The important difference is that even for Einstein, it was a heuristic step. It was not something, well, that is the way it is. It was a conjecture, and it's accepted only after experimental confirmation. So metaphysical reasoning is there in physics, but only as a heuristic step, not as a justified thing per se. Analogical reasoning is again along the same lines. Consider an example of analogy from ancient science. In a warm weather, we perspire and leave an earthy residue, sweat, that is salty. Seawater also gives out heat during hot seasons. Hence, seawater is salty. It's analogical reasoning. Something is happening, you just make one-to-one map and you say seawater is salty. This was no less than the man Aristotle said this. Modern science does not accept analogical reasoning as justified per se. See, Aristotle did not question it. That's the point. If he had said that it was okay, it's a conjecture. For ancient times, the ideas of approximations and that, well, it's a heuristic, that is not what, that's not their framework of thinking. So that's a very big difference between modern science and this. So they will modern science, but that doesn't mean modern science does not involve in analogies. In fact, very good scientists, they do use analogies. And in fact, cognitive historians of science say that analogical reasoning has been one of the most important elements in the cognition, not in justification, in the process of creating a new discovery. And there have been many important researches in cognitive history of science in this matter, that analogical reasoning is a very important reasoning. For example, Rutherford's model of atom and the heliocentric model of planets orbiting, they seem quite analogous. The inverse square law of force is quite a good analogy, not a bad analogy. But it turned out the atomic domain needed unexpectedly an entirely new theory of quantum mechanics. And this analogy, after some initial progress in old quantum theory, etc., it turned out not very fruitful. I mean, modern quantum mechanics doesn't involve it in a very big way. It is used sometimes, but sometimes the analogies are mathematical similarities. For example, differential equations for an LCR circuit and damped harmonic are identical in form. This has no direct physical meaning. It doesn't mean anything except it can be good for teaching. If students are familiar with damped harmonic oscillator, they have already done it, and they come across now a new subject, LCR circuit, then it's a nice pedagogical tool to at least recall them the analogy and do this, but warning them that it is only an analogy. It was only analogy per se is not a justification. However, in favor of analogies, in fact, sometimes they have been extremely powerful. And I'll give you an advanced example, advanced not for physics students, but if there are non-physics people in the audience, it's a bit technical. For example, Dirac, great scientist and who was among the creators of quantum mechanics, he solved the harmonic oscillator potential problem in quantum mechanics using only the fundamental commutator. You know, in quantum mechanics, observables are associated operators and they have commutators. And this is position and momentum commutator. It's a fundamental commutator of quantum mechanics. And he said that he'll get, without Schrodinger equation, the eigenvalues of the harmonic oscillator. And he got it. So, okay, that was okay. I mean, that was equivalent to Schrodinger things. So it was not an analogy at that stage. The analogy came later. Now, when Dirac was trying to quantize the classical radiation field, you know, a radiation field in space, you can always Fourier decompose, and then there will be coefficients, Fourier coefficients, and the radiation field equation that will get reflected in an equation for the coefficients. And those coefficients, as you probably all know, are oscillator-like equations. And here is the heuristic. Dirac postulated analogous commutators for these objects. There was no logical reason for it. I mean, they're just analogy that he had done this in single particle quantum mechanics. Now he did this for an entirely different context. But since they satisfied similar looking equations, he gave the same commutators. And lo and behold, it worked. It worked wonderfully. And in fact, That is the canonical quantization procedure in field theory that people adopted. So this is an amazing example of a mathematical heuristic in physics, that from some mathematical analogy, you heuristically go forward in physics, and sometimes it works wonderfully. So this is the sort of thing, this is one part of the talk. Modern science is better characterized by what kinds of reasoning it does not accept and what kinds it allows provisionally, subject to discussed earlier. Its acceptable modes of reasoning are no different from what we use in daily life. So, if somebody asks me what are the reasoning, the answer is, well, it's the same thing as common people use: deductive, inductive, and abductive, or abductive sometimes you can call heuristic reasoning. This is the reasoning we all use even in our daily life. That's what science uses. But in our daily lives, we also use the other kinds of analogy. Are not sensitive to the fact that they are different from these, whereas physics accepts the usual things, goes but does not accept. So modern science is characterized by the kinds of reasoning it has not accepted. And deductive reasoning, that's common. For example, given Newton's second law and law of gravitation, all the three Kepler's laws follow as a mathematics. That's the example of deduction. If Newton's law are they true, Kepler's laws are also true. So deduction is truth preserving. If the premises are correct, the conclusions are correct. But science is not all deduction. In a sense, even mathematics is not all deduction. For example, Euclidean geometry is a deduction. We generally feel mathematics is all very strictly deduction, and of course it is most part of it. But right at the foundation, it is based on a few postulates which are given. They're not proved. The difference, there is a very important difference, that the starting premises, difference between maths and science is that the starting premises on which a scientific deduction is based must be checked against nature, whereas postulates in mathematics are a free choice. There is no obligation to check if they have anything to do with physical reality. Actually, this difference was not so obvious to even early modern scientists, Newton, and in those times, this difference in science and maths was not so clear. It started getting clear only towards in the 19th century or so, when it turned out that mathematics is its own premises, with non-Euclidean geometry and things of that kind, that you can start with some premises. It's a matter of your invention, provided they are mutually consistent, and you can build a mathematical system. And whether it has anything to do with reality, that's not their problem. And it so turns out that some of the mathematical structures, for reasons that nobody knows, turn out to be of immense useful to physics, but that's a different matter. How then to obtain the premises on which a scientific deduction is based? Said simply, this involves induction from observation. So induction, as you all know, is from given finite number of observations, you generalize the results. So experiments on free fall in vacuum, large number of bodies show that they have the same acceleration. By inductive reason, we can say that acceleration is independent of the mass. But it isn't as simple as that. This is the kind of thing Francis Bacon, for example, this naive inductivism, as it is called, was proposed by Francis Bacon. He was, you can say, the first philosopher of modern science and so on. But it isn't as simple as that. Observations usually give very complicated data, and simple induction is not enough to do. So we are forced to use heuristic reasoning. What is heuristic reasoning? Well, you guess ideas. Not that you can read off from data, but to guess ideas. And this the so-called hypothetical deductive method of science, which is a name for heuristic. And sometimes there are several hypotheses that work. It's not that, you can try at that stage of experimental data, there could be various hypotheses that might work. And we choose the one that explains a greater variety of observations. I think if you go into the history of special relativity, you will see that the inference to the best explanation was, was Einstein's rather than Lorentz and so on. So we choose that seems to explain things a very wide variety without making ad hoc or sort of unnatural, contrived assumptions. So there is this tacit thing among scientists, inference to the best explanation. Now, this kind of thing, heuristic reasoning may employ intuition, analogies, metaphysical ideas, beauty, coherence, whatever ideas. Dirac said that, there are great scientists who are helped by this kind of reasoning. Dirac said that the equations of physics must look beautiful, whatever he meant by beauty, because sometimes it's not easy to quantify what one means or even say what that means. But one very fantastic example of heuristic reasoning is Einstein's calculation of volume dependence of entropy of thermal radiation. You see how Einstein arrived at the photon concept is a nice example of heuristic reasoning. He determined volume dependence of entropy of thermal radiation. And this was found to be mathematically similar to that of molecular gas. And since this molecular gas, gas consists of the molecules, that is discrete units, Einstein just proposed that radiation too had discrete units. This is not either inductive logic or deductive logic. This is heuristics. In fact, Einstein's paper itself is titled A Heuristic Hypothesis. So I'm taking the word heuristic directly from no less a person than Einstein. And he used that heuristic hypothesis to explain, and still it was not accepted because it was going against that thinking. It took a long time before almost 2 decades, just under 2 decades to accept the idea of photons when Compton effect and things like that were discovered. In general, great scientists, people like Einstein or whosoever we think are great scientists, they're distinguished by their powerful heuristic capacity, which is basic to their creativity. So I say this advisedly, this line as a teacher and a physics educator, I want to say that I have deliberately not used the word ability here. I've used the capacity. Because if you say scientists are gifted with ability, then it's sort of educationally not a very healthy thing to do, because then, I would say, well, I don't have that ability and somebody else has that ability, and you feel discouraged. So that word ability should be, at least among educationists, as a feeling that you should not use it too easily. Capacity is a good word because capacity can be built by hard work and so on. So you don't have to be born with that. You can build up capacity. That's why we say capacity building programs for students or teacher or whatever. So capacity is not something innate, but ability gives the connotation of innate. It's best to avoid that. Anyway, that was a digression. The point is that this intertwining of theory and experiment that I discussed a very simple schematic of what goes on in science. The actual thing is much, much more complicated. It's very complex, which is not easily, which cannot be given a simple methodology. Experiments are now, modern experiments are very highly theory driven. It is not that you make observations and then you start, no, it's not that way. Experiments are highly theory driven. Their whole language, the whole apparatus, equipments are built based on a certain guided by theories and so on. So it's a very complicated game, but that does not subtract or detract from the objectivity of science. Science still remains objective because still, even if they are theory laden, if they don't work out, you do reject those theories, etc. So still the objectivity of science still remains. To summarize, reasoning in modern science rejects teleology and anthropocentrism and adopts a combination of deductive. This mixed reasoning is used to develop increasingly detailed models of the world whose deductions So now I'm coming to the next part of my talk. And this is, and I'll take the questions at the end because I'm running short of time. So I think, let me now go ahead with a little more speed. The point I'm trying to make that, well, now we have accepted it is not teleological, it's not anthropocentric, and it's heuristic, etc., etc. All right, that's not enough to characterize physics, for example. The models used in physics, we develop models in physics. That is all right, that informs all those models, but that's not enough. The subject is characterized by different explanatory frameworks, kinds of approaches. Within the same reasoning, there are different kinds of approaches. So we are not departing from reasoning, but we are within that have different approaches. And by framework, we mean a broad view or approach to an explanation. They differ across some subjects, and they can also change as science progresses. One common trend, I will not do anything about chemistry and biology, I'll be restricting to physics only, but I just want to say one common thing that the 20th century and 21st century saw one common trend that science is getting more and more reductive. That means even chemistry, you explain macroscopic thing in terms of microscopy. Now, quantum chemistry becomes basic to many chemical phenomena. And biology is genetics and molecular biology. So the arrival of these new modern physics subjects is making even these subjects, all natural sciences, more and more reductive. Once again, no value judgment whether it's going to, there's going to be some limitation of it. I don't know, but that's the characteristic at the moment. So now I'll change the wavelength of this talk, and I'm going to now do something. Please pardon me if I overspill over a few minutes, because so we now describe some explanatory frameworks in science. Each framework is a pair of seemingly opposite, but usually complementary aspects. So this is something I have classified as a teacher, and I means we are a group of 3 physics educators. I'm going to name them later. And this is what we have classified the subject at the BSc, MSc level, the kinds of approaches that are adopted. I once again say it's too ambitious to say what are the different approaches in the whole of physics, in the whole of current sophisticated. No, we are not aiming that. Our aim is educational up to MSc level. What kind of approaches should we point out to our students? All teachers and students go through all these things, but what our aim is to give a holistic view of these approaches, and we feel that that would be useful. That is the educational thesis we have in mind, that if you present these approaches in a holistic way, maybe it will be useful to students. So one thing is they are not mutually exclusive. For example, if I'm doing scattering theory in quantum mechanics, it's time dependent, let's say scattering theory, then it will be time dependent, microscopic, probabilistic, local. So a given subject cuts across all these things, approaches. Also, we must be modest. This classification, we don't claim at all to be unique, or even that it's, as I have said many times, there would be different physicists will use different frameworks, and they may use additional frameworks besides these, whatever it is. This is just the idea of our group. Now, 2 distinct themes in physics, dynamics and equilibrium. So that is first framework. What is dynamics? Dynamics in physics, generally problems pose themselves as either dynamical or equilibrium problems. Dynamics is about change. It involves differential equation, time as independent variable. The dependent variable may be particle in a gravitational force or a charged particle on its force. There will be some differential in Newton's second law, a differential equation, second order differential, etc. Or it could be, differential equation for an electromagnetic wave, for electric field component or magnetic field component. Again, it's a dynamical thing where we want to see how it propagates in time. or it may be the wave function of a wave packet. I mean, there may be a wave packet in quantum mechanics governed by psi of RT, and how does it move in time? How does the wave packet move in time? So these are typical time-dependent questions. What I am suggesting is that these points be brought before the teachers may bring these points before the students. That laws are not enough. Solving dynamical always needs some initial condition. A trivial point for physicists, but it is necessary for students to know this. For example, under the same law of gravity, a particle may go just up or along a parabolic trajectory depending on the initial velocity. So that is the equilibrium. Translational and rotational mechanics, it means net force and torque is zero. So equilibrium frameworks are different. Equilibrium thermodynamics is a different notion. It means the thermodynamic variables are time independent. The mathematical equations of equilibrium thermodynamics do not contain time variables. See, thermodynamics is a macroscopic subject. It doesn't go into the atomic constituents of matter. And therefore, although the macros, internally time-dependent things are going on, but equilibrium thermodynamics deals with only the variables which are time independent. And therefore, there is no time variable in equilibrium thermodynamics. But thermodynamics does deal with processes. It does deal with changes. So this looks paradoxical. It does deal with changes, and yet there is no time variable. How? We introduce the notion of quasi-static process. It's an infinitely slow process where the system passes through succession. So this is how equilibrium thermodynamics gets rid of time and makes it an equilibrium framework. And then it doesn't give any value of any property. It basically gives you relations between properties, or it gives you directions of change, for example, entropy law, etc. etc. We all know very well. Equilibrium in statistical mechanics is, again, how does it get rid of time? Because the bulk system is in equilibrium, but the molecular configurations are changing all the time. So how does it deal with it? It deals with the artifact of ensemble theory. We imagine a large number of copies of the system which has the same macro state, but in different micro states and associated with that single macro state. Each member of the ensemble is represented a point. So, there is a phase space. Now, it's a physics audience, so I don't need to explain what phase space is. There's a point in the phase space of that system. And this ensemble has different micro states. So there'll be different points in the phase space corresponding to this ensemble. And therefore, there'll be a density function for the ensemble. And equilibrium means this density function is independent of time. And the important point is, you see, physically what we measure is a long time average of a physical point. But theoretically what we do is to take the ensemble average. It's a bit difficult point. I will not get into it. And also a very sort of endless point of endless debates. It's called ergodic hypothesis. And statistical mechanics, actually, this equilibrium goes much beyond thermodynamics. It not only gives averages of thermodynamics, but it also gives fluctuation. And there are many things that StatMech can do which thermodynamics cannot. So let's have a look at the microscopic versus macroscopic theory. Microscopic theories, as we have always said, physics basically is a reductive science. It aims to explain macroscopic constants in macroscopic properties in terms of the properties of microscopic. That is what the reductionistic program of physics means, explaining bulk properties in terms of constituent properties. Now look at classical continuum mechanics. It is macroscopic, but it doesn't really go into the micro level, although it goes to every little element, but that element at macro, not micro. So similar remark applies to macroscopic electrodynamics. On the other hand, kinetic theory is a proper classic example of a microscopic approach. it does go into the microscopic details of molecular energies, number density, size of atom, and then relates it to the macro variables of pressure, temperature, and this. So these are some of the important points about macroscopic versus microscopic framework. Thermodynamics is macro, I have already told you. Statistical mechanics is macro, but still it does go into the picture of molecules, the energy level of their population. Kinetic theory goes into the detailed molecular dynamics of the system. And now currently there's not much difference between non-equilibrium statistical mechanics and kinetic theory, which I'll not get into. But these are the kind of important frameworks in theory. Now, at the microscopic level of atoms and molecules, and if you go to the constituent, then classical physics doesn't work. It has to be regarded, replaced by quantum theory. So what is regarded an elementary constituent depends on the scale. For ordinary scales, atoms and molecules are the elementary constituent. So for example, when you are explaining viscosity or heat conductivity in kinetic theory, then your elementary constituents are not electrons and stuff like that, just atoms and molecules. That is the elementary constituent for kinetic theory to explain viscosity. But if you are going into atomic structure, atomic collisions, molecular collisions, their spectra, then the elementary constituents are electrons and nuclei. If you're going into nuclear physics, then you will have protons and neutrons as their elementary. And at the still lower scale, the current scale of interest in particle physics, the elementary constant. So what this elementary constituent is depends on the scale of interest. That's all I'm trying to say. And the lower the length scale, the higher is the energy of the probe required. For example, if you want to probe the structure of an atom, you Rutherford use alpha particles of a few MeV. But if you, in the similar experiments, Rutherford-like experiments, scattering experiments, electrons of much higher energy were used to probe the structure of a proton because it's a different scale altogether. And the quark constituents, from these deep inelastic scattering experiments, this quark theory was kind of inferred. An important feature is that this microscopic theory at a particular scale works even if we do not consider the final. This is a great point in physics, very intriguing really. Nature seems to admit of effective physical theories. For example, when I do kinetic theories, I don't need to worry about quarks. Why not? Because it's an aspect of nature that is not something obvious. For example, the theory of quantum electrodynamics, it seems to work exceedingly well up to the length, to a very small length. Although at still lower lengths, we do not know what their theory is. Nobody knows what the correct theory is. There may be lots of speculation, but really any established theory is yet to arrive. Still, QED works fine. This is incredible. This is not to be taken, as something obvious. But anyway, this, a deeper understanding of this requires certain things in modern physics that we cannot get into. Now, in general, I would say a microscopic description is more predictive, but dependent on the available theory. On the other hand, macroscopic laws which are governed, they are more robust and remain true. They are less predictive, but they are more robust. For example, the laws of thermodynamics discovered in mid-19th century. Third law was a little later, 1930s or so, but by 1850s, 60 or so, the first two laws had arrived, and they have remained. They have survived major. Various things change, but not these laws of thermodynamics, at least at the most probable level. Now I turn to the next framework, the deterministic versus probabilistic framework. In deterministic framework, there is no element of chance in the basic laws. For example, Newtonian mechanics is deterministic. What does it mean? Given initial conditions, the laws determine the trajectory of each particle. But note, given initial condition, that's very important. Provided, of course, all the environments must be known. Otherwise, you can't, the equations are there, but you can't solve them. So it's deterministic. In principle, you can solve. It may be difficult, that's a different matter. In fact, this view applies even to classical fields, such as electromagnetic field, the wave equation. Only it's far more complicated mathematically because it's a system with infinite degrees of freedom. So the required boundary conditions are not simple as this. For a single particle, there are 6 conditions. It's not as simple as this. They are more complicated. A lot of involved mathematical physics, Cauchy conditions and stuff like that, where you have to, in 3-dimensional space, for example, a 4-dimensional space-time, on a hyperplane, you have to give the values of fields and their derivatives, etc., etc. Those are matters of detail, but the philosophical point is that even this is deterministic. In short, in the classical view, the present state of the universe is known. I think you all know Laplacian determinism. Laplace is arrogantly said to have made this statement. Of course, in practice systems, real deterministic thing you can work out only for small degrees of freedom, like translational motion of the center of mass of the body, or at most rotational degrees of freedom for a rigid body, governed by Euler's laws of rotation, etc., etc. So, probabilistic framework, therefore, sometimes becomes a necessity. It may not be fundamental, but it's a necessity. For example, internal states of macroscopic system. It's obviously not practical to track the trajectory of each particle. So then deterministic framework is then perforce replaced by a probabilistic framework, even when the microscopic constraints follow deterministic laws. So classical statistical mechanics and time are a result of this circumstance. The basic laws are deterministic, but what can they do? You can't, it's just impractical. So you have to use probabilistic notion. But interestingly, the very large number of degrees of freedom is a very, we would think, well, that's an impossible situation, what to do with it. Fortunately, at least in equilibrium, there is an important feature, randomness. Again, a very subtle concept. I'm doing it too lightly. The randomness means there's no real privilege about one configuration over the other, etc. For example, when teachers teach Maxwell's velocity distribution of molecules in a gas in second year BSc or third year BSc, I think we should emphasize to the students how important is this assumption. In fact, no physics goes into the derivation of velocity distribution. We don't need to know what the interaction is, except that there should be an interaction. And then mere randomness and some general assumptions of homogeneity just yields the Maxwell's velocity. What a fantastic thing. One could not have thought of this because the system is so complicated, a very number of constituents, and still here we are getting a correct velocity distribution in equilibrium. Also in statistical mechanics, in the so-called microcanonical, we use the equal a priori probability, something similar. One point that sometimes college students miss, and I think teachers might want to give this point to the students, that deterministic laws lead to predictability, provided the initial conditions are known with absolute precision. But in practice, there's never absolute precision. There's always some margin. So it's again a practical point, but very important point. There's always some margin of error. Now, in some nonlinear systems, it can happen that in certain regime of the values of its parameters, this initial error exponentially amplifies with time. In such a case, the initially closed particle trajectories in phase space diverge away in time. So this hypersensitivity to initial conditions leads to loss of long-term predictability and is known as, so, one important point of determinism, see, people used to confuse before this topic that determinism means predictability. This topic of chaos has said, do not confuse determinism with predictability. Yes, often it is. Determinism deterministic equations give you predictable, like the motion of a comet, but not always. Sometimes in some equations, it can lead to chaos because of just a little change in initial conditions. The trajectories will go on diverting and they will not stay closed in the phase space. And chaos can characterize simple system governed by logistic equation. You probably know it. It's a population equation in a limited environment. Or even complex systems. That's how it was discovered. For example, weather described by coupled nonlinear equations. So it can exist anywhere. It has to be certain nonlinearity is essential for this thing to happen. To sum up, classical physics is fundamentally deterministic, though practical constraints can lead to loss of predictability, either because of this chaotic chaos point or because of the points earlier stated regarding the fact that there are just too many constituents to worry about. So, yeah, but quantum mechanics is fundamentally indeterministic. It replaces trajectory-based picture. I will not repeat, it's all routine, known to every physics student and teacher. So I'll just run through the slide, wave function. It has only probabilistic information. And this point that you can only talk of probabilities, it is not like for classical statistical kinetic. It's not inherent. It is inherent to the theory. It's not a question of practical need. It is true even for a single particle. So that shows it is not a question of practical problem. It's not a practical constraint. It's inherent. It's a feature of nature. But one important point is that it's not all haywire. It's not all, you can't do anything about it. No, it does satisfy a clear time-dependent Schrodinger equation. And Schrodinger, so if you have given psi r at the initial point, you get psi r to determine for all time, provided the environment is known. So we have a kind of determinism, I have to put it in quotes, of probability distributions. It's not that just everything is lost. For example, in a double slit experiments, you send a path of, you can't say anything about a single electron. But when it comes to its probability distributions, the overall diffraction pattern, that is not erratic. I mean, given the experiment and given identical conditions for the experiment, you will get the same diffraction pattern. Though for individual electron, it is probabilistic in nature. So this is the framework, deterministic worker. Now, how much time do I have? Do I have 5 minutes more?
5 minutes is okay, Professor Arvind Kumar.
Yeah. So I think now I'll have to skip this last point. Local versus global frameworks. I think teachers, all I would request teachers to tell the students, is rarely told an obvious point in the BSc, MSc classes, that Newton's law is local. F at a given point, at a given law, is Lorentz force. It's local. Force at a given point is electrical at that point, V at that point, cross B at that point. And F at that point is acceleration, at that time. You see, A is R, so R is anyway there. So for a particle. So it's a local thing, and this is very important because there are many misconceptions based on not knowing the fact that Newton's law is a local law. It's an obvious fact. But in theoretical physics, there are many other things which I cannot go into it. For example, there are global objects, like I have already told you, the action principle, and they satisfy certain global laws. So variation principle, you may want to say it's a global law. S satisfies, S is an extremum. But I have already told you that it's equivalent to a local law. So there's a nice interplay of local and global frameworks, which I don't have time to go in. And the reason this is very important in current physics is because of its connection with gauge invariance. which I'm sorry I don't have time to get into, that the Lagrangian of the system, generally it's invariant under phase transformation. It depends on this phase, whether it is the sky, whether it is global, is independent of x or depends on it. Then if it is independent of x, is global invariance, but many free Lagrangians, Dirac would not have this. And then you have to add fields to make, if you want, local gauge invariance. And this is an important heuristic in current particle physics. Using local gauge invariance as a heuristic requirement to develop theories, and the standard model in particle physics actually is a successful result of this effort. And as against this, there are topological ideas in physics which are nowadays coming in a big way in physics. But a simple example is Gauss's law, which relates electric flux through a closed surface. This flux is invariant under any, if it's a closed surface surrounding a charge, you make, as long as it is closed, you don't put any holes in it, or you transform it anyway. But sphere you make an ellipsoid, doesn't matter. The Gauss's law will still hold good. So it's a kind of very elementary example of topological ideas in physics. Similar ideas are there with Ampere's law. And now, of course, this, as I told you, this topic is coming in a big way on topics that we cannot do it here. And just one final point that I've been saying, locality of basic laws, even quantum mechanics is a local, Schrodinger equation is a local equation, etc. However, in more recent decades, there is this entanglement concept in quantum mechanics, and it does show that there can be non-local correlations in entangled quantum states, provided they do not violate relativity. So the non-local correlations in current quantum mechanics that experimentally have been found, they were a sort of uncomfortable thing. I mean, to Einstein, who believed in local realism, it was not an acceptable thing. But now it's no longer a philosophical status. It has come down. All these issues have come down to experimental verifications, and these non-local correlations have been verified, as far as I can say. And therefore, one should not think that locality means there cannot be non-local correlation. That's only a caution. We cannot go into the details. So the concluding remarks are, the ideas about reasoning modes in science are part of implicit now. All teachers, whatever I said is all known to teachers. I just summarized what is known to teachers and scientists. But it should be useful to teach them explicitly, since young college students. We should not assume that, well, they would know, because you see, the experts imbibe these things over several years, which will not be obvious to beginning students. For example, an often used statement is a body released free tends to reach the point of minimum potential. This statement is often said in the class. Nothing wrong with it, but it can carry a sort of tell you, it tends to reach, as if it is wanting to reach the minimum potential energy. Better to say locally. At every point in the motion of a particle in a conservative system, the force is in the direction of greatest. When you convert something local, that the force at this point is in this direction, gradient of potential energy minus of that at that point, then there is no question of triviality or anything. Similarly, anthropocentrism, in fact, is, physics education research shows it's one of the most important sources of pitfalls in learning. Because especially in relativity, the frame of reference, with all synchronized clocks, a very objective thing, is often casually described by the word observer. And students pick up the human-like connotation with that word. So human-like association with this widely used word observer is basic to many pitfalls in Galilean special relativity. Actually, at the Homeova Center, we did a lot of research in Galilean relativity on this, and in special relativity, the University of Washington Seattle group has done a lot of work on this, how students confuse the meaning of the word observer, and in fact have very, very flawed understanding of the relativity of simultaneity, and so on in this. So anyway, I do not have time to talk about the pitfalls, which will need another discussion. Same remarks apply to explanatory frameworks. They are part of normal teaching of physics, but students learn them piecemeal and do not have the expert overview. Giving a holistic view can help students enhance their appreciation. See, when you see things as a whole, you get a little better perspective of the subject. So that's our modest suggestion to teachers, that these frameworks that they all are familiar with, a holistic overview should be given some time to students in the course of their education. In general, making the implicit expert knowledge explicit in instruction is an important trend in current science education research. In current science education studies, many of them emphasize this fact that experts know something, and the job of science education to take the implicit knowledge and make it explicit in classrooms. And so my talk was a modest attempt in this direction. So I'll just acknowledge that this presentation draws on an article by K.K. Mashur, Anvesh Majumdar, and myself. We're preparing it. And part of this talk overlaps with my talk on the Teachers' Day. So first part of reasoning, those who attended that talk might find some of the things repetitive, because part of my reasoning section of this talk overlapped with that. But the explanatory framework part is new. And it's a pleasure to thank my collaborators, Mashur and Anvesh, of the Physics Education Group, for discussion and support. I leave you with some, only a very few references. I would very strongly suggest that teachers recommend this to explain the work, The Discovery of Modern Science by Arvind. In fact, this talk is the reasoning part of it, not the explanatory framework part. It's quite inspired by Stephen Weinberg. I mean, we have to try to put it in our own words, but the basic inspiration is from this book. And the quote was from this second book by, I have not written the author's name. This again by Weinberg, Dreams of, I'm sorry, I did not write the name of the author. This is another good book, giving an overview of physics. And if you teachers wish to go to details of the learning barriers that I was talking towards the end, then they can see this special issue on physics education, October 2011, where these learning barriers have been discussed in great detail. So with that, I thank all the organizers, Professor Dhruva and Professor Somak Chaudhary, for inviting me to this talk, and thank you very much. That's all I have to say.
Well, thanks very much, Professor Arvind Kumar, for a wonderful talk and many, many points for us to reflect on as we teach. And I'll open the session for questions by, you put your hand up. If there are not too many hands up, you can just unmute and ask. Ambrish would like a question. Please unmute yourself and ask.
Hi, Professor Kumar. Am I audible?
Yeah, you're audible.
Yeah.
Thank you very much for a wonderful talk. So the question that I want to ask may be kind of difficult to express myself what I want to convey, but I'll try my best. So you explained about the nature of physics, that it is reductive in nature. That means we can explain the properties of macroscopic objects in terms of the microscopic constituents that it is made of. So although that seems fairly intuitive, why can you explain why the nature of physics is like that and not the other way around, in terms of we can explain the properties of microscopic things from the macroscopic things?
I do not know if I can answer that question. I mean, physics is reductive in nature. I mean, that is, the downward, it's the causation upward from microscopic to macroscopic.
Yes.
That's the kind of causality, or I shouldn't say causality, I should say the reductive approach. that has worked.
Yes.
Whatever works in physics is what is adopted.
Okay.
So, and it's the reason we take microscopic approach is because it's more predictive in nature. Macroscopic laws are much less predictive, but when they are explained in terms of a microscopic picture, you can use the microscopic picture not only to predict what you see it macroscopically, but also various other things that you may not have observed. So microscopic theories are far more predictive than macroscopic theories. And the simple answer to the question is the reductive approach has worked in science. And nothing succeeds like success, as they say in life. So in biology also, for example, there were why has biology also turned reductive? Because that's the way it has worked. I mean, it has been able to explain and do far more predictive things than earlier biology could do. So I don't know anything more than this. If there's a better philosophical explanation of it, I do not know.
Okay.
Yeah.
So this is about the discussion of about the human mind. So we look at our human mind, and there is this discussion of free will. So there is the probabilistic approach of physics and the deterministic approach. So do you have anything to weigh in on that?
No, I would not comment on.
Okay, maybe that's not a good
the
question.
domains that I have no idea about, and those are very tricky issues. You are talking of the volitional domain. As I said, my talk is entirely restricted to non-volitional, natural sciences.
Yes.
When it comes to mind and motivation and free will, these are very difficult issues, I think, and it's best.
There's a hand raised by Pura Ram. So would you like to ask your question? Unmute yourself.
Yeah. So I have no, I mean, these are very important. Your question is very important, but it's not something I can answer. Questions on free will and consciousness or human mind, they are so far not there, you can say, at the edge of natural sciences, the neurosciences and these are very important areas, consciousness studies and so on. But at the standard established natural sciences, they are not part of it.
Yes, I understand.
Yeah.
Okay, one last question by Pura Ram.
Yeah. Yeah. Good evening, sir. Is my voice audible?
Yes.
Yeah. So, wonderful talk and very good insight. My question is related to the application of the, we can say, any reasoning in the domain level. So, when we thinking about the micro domain, that means phenomena is going on very low time scale phenomena. And when we discuss in macro level, that means phenomena is average out and give the proper results. So how we deal with the time domain versus phenomena domain?
Very good question. That is what I meant by long time average. The microscopic timings are very small, but at the macro level, when we do experiments, our times are not femtosecond, etc. We are measuring temperature of gas, etc. So the space and time levels at the macro levels are much more, even if they are small macro wise, they are far, they have millions of molecules, and the time scales of molecular, as you rightly said, are very small. So it always amounts to space and time averages. If you teach electrodynamics, macroscopic electrodynamics, that is what is done. You do not. Why do we regard macroscopic matter as continuous? Actually, at the lower, at a certain scale, it is continuous. So similarly, you have to take certain time averages of something which is going very first. That is how from microphysics you come to macrophysics. A good example will be to arrive at macroscopic Maxwell's equations from microscopic Maxwell's equations. And this job is not easy. It's quite a complex thing, very complicated thing to take time averages and space averages of these things at the lower level.
Okay.
Simple answer to your question is macroscopic things are time and space averages of the microscopic things that are there.
Yeah. But as we go in low time scale, then complex.
However, that does not mean you do not. If you are doing a microscopic experiment,
Right.
if you are doing electron scattering experiment on an atom and you are doing some kind of time resolved experiments, then of course you are probing the microscopic atom levels.
Right.
But generally speaking, macroscope that is microscopic quantum mechanics. So quantum mechanics, when it deals with electron atomic stability, it's not averaging on anything. It is
Right.
doing electron atom scattering at that length at that time.
Right. Thank you so much.
Okay, thank you very much, Professor Arvind Kumar, for a wonderful talk and a very pleasant evening and a lot of discussions. So thank you very much. So we'll close now. Yeah. Thanks.
So,
we'll be in touch later.
can I leave now?
Yeah, sure. Thank you very much. Thanks to all the participants who
Thank you.
logged in, and thank you very much.